All right, IP services. Okay, ARP vulnerabilities. Okay, host broadcast. 1 second, yeah. Okay, host broadcast and ARP requests to other hosts on the segment to determine the MAC address of hosts with a particular address. And then the host with the matching IP address in the ARP request send back as an ARP reply. All right. So any client actually can unsolicited ARP reply call a gratuitous ARP. When a host sends gratuitous ARP, other hosts on the subnet store the MAC address and IP address contained in the gratuitous ARP in their ARP table. This feature of ARP also means that any host can claim to be the owner of any IP or that MAC address. And a threat actor can poison the ARP cache of devices on the local network and also creating an middle of man in the middle, yeah, attack to redirect the traffic. Okay, all right. So ARP cache ARP can be used to launch various man-in-the-middle attacks. Yeah. So like PCA, right, require the MAC address of its default R1. Therefore, it sends an ARP request for the MAC address of 192.168.10.1. Later, R1 update its ARP cache with the IP and MAC addresses, yeah, of PCA. And then R1 send an RP reply to PCA, which then update, yeah, its ARP cache with the IP and also MAC addresses of R1. Yeah. So the threat actor sent two spoof gratuitous ARP replies using its own MAC address for the indicated destination IP address. Indicated mean back to him. Yeah. PCA updates ARP cache with its default gateway, which is now pointing to the threat actor. Threat actor host MAC address. So R1 also update ARP cache with the IP address of PCA pointing to the threat actor MAC address. So the ARP poisoning attack can be passive or active. Passive ARP poisoning is where threat actor steal confidential information. Active ARP poisoning is where threat actor modify data in transit or inject malicious data. Okay. So this video will explain an ARP spoofing. All right, let me share the video of ARP spoofing.
Welcome to ARP spoofing. This is gonna be great. To get started, I've got PC1 here that wants to communicate to the web server. PC1 is on the 192.168.1.0 network. The web server is on the 2.0 network. For PC1 to get there, we've got to make our way through this router, which is R1. R1 is acting as the default gateway of our network with IP address 192.168.1.254. R1 has the MAC address ending in 9902. So PC1 is going to have to communicate with this router in order to make its way to the web server and get a response back. Now, quick recap of how ARP works. In order for PC1 to get to the web server, it needs to know the MAC address of its default gateway. So let me open up PC1, go to my command prompt, and we're going to do an ipconfig /all. And with our ipconfig /all, we'll see that PC1 has its MAC address of B0EE. It's got an IP address of 1.10, and it knows the default gateway IP address. It knows the router is 192.168.1.254. However, if I take a look at my ARP cache with an ARP space -A, there's nothing in there. It doesn't know the MAC address yet for router R1. So if I were to send out a message, like maybe I want to ping 192.168.2.100, that remote web server, the first ping's going to fail. And that's because my PC1 is resolving with the who is 1.254. And by the time that ARP resolution happens, the first ICMP ping message timed out. That's okay. The other three were successful. And now when I check out my ARP cache for an ARP space -A, we can see that my default gateway 1.254 is known as MAC address 9902. Now this is awesome. Lab is complete. What if it's not complete? Well, just to kick it off, one last thing to try out here. I'm going to open a web browser on PC1. And now that we have layer 3 reachability to that server, let's go and use port 80 of TCP and hit that server at its IP address. And we have connectivity on port 80 using TCP. So this is great. But when does that threat actor come into play? How about now? My threat actor, I'll open it up and go to my command prompt, has an IP address and MAC address already. And this is just a normal user on the network that has too much time on their hands, maybe. This user has a MAC address of 2088. It has an IP address of 1.20. And it also understands that the default gateway is 1.24. But what if this threat actor wanted to be a man in the middle? Well, we can make it happen. I'm going to go ahead and go over to my router R1, and I'm going to go into my interface that's connected to this 1.0 network. I'm going to grab that MAC address. And then we're going to go back to that threat actor machine. Don't worry, threat actor, we're going to give you a gift. On the threat actor's interface, we're going to change its MAC address to spoof the MAC address of the default gateway. Now that it has the MAC address of the default gateway, let's have some fun. I would send a gratuitous ARP over to PC1. Because they don't have the ability to do that here in Packet Tracer, how about we send a constant ping? And this constant ping is going to be talking with the IP address of PC1. And you know what? Who's the source? Us. Us, threat actor machine, now with this spoofed MAC address, which would be the default gateway. And I want to show you something. On PC1, let's take a look at our ARP cache now. ARP space -A. We see that 192.168.1.20, hey, check it out, has that MAC address of the default gateway. And also, let's go over to the switch, our Cisco networking switch. Let's verify our MAC address table. Show MAC address table, dynamic. And let's take a look at the MAC address learned off of port 2 and check it out. Off of port 2 is the MAC address now of the default gateway. So now what happens when PC1, which we're going back to right now, tries to browse the web? Open our web server up. Let's go back to 192.168.2.100. Enter. It's just timing out. You can see there's no activity lights moving here at the top regarding this traffic. It's a timeout. But now comes the fun part. If our threat actor is running a type of analyzer for traffic, such as this network sniffer sitting here right outside, I can go into and click on one of those messages, and I can actually scroll through and read through the headers, as well as even be able to read through the data fields of the traffic. And what we can see here is the source IP was 1.10. That was PC1. The destination IP was meant to go to 2.100. Well, then how was it switched over to the threat actor? Because the switch thinks that off of port 02 is MAC address 9902. The spoof was successful. When I scroll down, you can see here in layer 4 info that this thing was targeting port 80, destination port 80, source port 1026. Man in the middle attack, successful. And if we had better threat actor software, we could literally capture this data and at the same time be sending it onwards to the default gateway ourselves, acting like everything is just fine, using a beautiful but unethical man in the middle attack.
Thank you. All right. Okay. So we got one more video after this. So back to the lecture. All right. Okay. So DNS attacks. The domain name service, or DNS, yeah, DNS, define an automated service that matches resource names such as www.cisco.com with the required numeric network address, such as IPv4 or IPv6 address. Okay, that's the function of DNS. It includes the format for queries, responses, data, and user resource record, yeah, to identify the type of DNS response. Securing DNS is often overlooked, yeah. However, it is crucial to the operation of a network and should be secured accordingly. DNS attack include the following item: DNS open resolver attacks, DNS steal attacks, DNS domain shadowing attacks, and finally, DNS tunneling attacks. Okay, DNS open resolver attack. A DNS open resolver answer query from client outside of its administrative domain. DNS open resolvers are vulnerable to multiple malicious activities as described in the table below. All right. Okay. DNS resolver vulnerabilities. Okay. So the first is DNS cache. Yeah, DNS cache poisoning attacks. So what are these? Yeah. Threat actors send spoof and then falsify record resources of RR information to a DNS resolver to redirect user from legitimate site to malicious site. DNS cache poisoning attack can all be used, yeah, to form the DNS resolver to use a malicious name server that is providing RR information for malicious activity. Okay, so this was done on DNS cache poisoning attacks. So what I mean by DNS amplification and reflection attacks? Threat actor use DOS or DD or DDoS, yeah, attack on DNS open resolver to increase the volume of attack and also to hide the true source of an attack. So they create the volume. Yeah. Threat actors send DNS messages to the open resolver using the IP address of a target host. These attacks are possible because the open resolver will respond to query from anyone asking a questions. So meaning every second they will create a dummy access, maybe 1,000, maybe million, every single second. All right. So that's normally, and normally this kind of the attack. Yeah. So they create the high volume. All right. So the third one, DNS resource utilization attacks. A DOS attack that consume the resources of a DNS of a resolver. This DOS attack consume all the available resources to negatively affect the operation of the DNS open resolver. The impact of this DOS may require the DNS open resolver to be rebooted or services to be stopped, and also finally asking for the restarted. Okay. All right. So DNS steal attack. To hide the identity, threat actor also use DNS steal technique described in the table below to carry out their attacks. So DNS steal technique, fast plug. What this fast plug? Threat actor use this technique to hide their phishing and malware delivery. Yeah, site behind a quickly changing network of compromised DNS hosts. The DNS IP addresses are continuously changed within a minute. Botnet often employ fast plug technique to effectively hide malicious server from being detected. Double IP plugs. Double IP plug. There is another techniques Threat actor use this technique to rapidly change the host name and change the host name to IP address mapping and also change the authoritative name server. This increases the difficulty of identifying the source of attack. Next, domain generation algorithm. Threat actor use this technique in malware to randomly generate domain names that can then be used as rendezvous, point to their command and control CNC server. All right. DNS domain shadowing attacks. Domain shadowing involve the threat actor gathering domain account credential in order to silently create multiple subdomain to be used during the attack. These subdomain typically point to malicious server without alerting the actual owner of the parent domain. DNS tunneling. Threat actor who use DNS tunneling, place non-DNS traffic within DNS traffic. This method often circumvent security solution when a threat actor wishes to communicate with bots inside a protected network or exfiltrate data from the organization. This is how DNS tunneling work for CNC command sent to a botnet. Okay, so first the command data is split into multiple encoded chunks, and each chunk is placed into a low-level domain name level of the DNS query. Third one, because there is no response from the local or network DNS for the query, so what happened? The request is sent to the ISP recursive DNS server. And next, the recursive DNS server will forward the query to the threat actor authoritative name server. The process is repeatedly until all the query contain the chunk of containing the chunk of are sent. When the thread actor's authoritative name server receive the DNS query from the affected devices, it send responsive for DNS query, which contain the encapsulated and also encoded CNC command. The malware on the compromised host, recombine the chunk and execute the command hidden within the DNS record. To stop DNS tunneling, the network administrator must use a filter forward that inspect DNS traffic. Pay close attention to DNS query that are no longer than average or those that have a suspicious domain name. So DHCP. DHCP server dynamically provide IP configuration information to client. In the figure, a client broadcasts a DHCP discover message. The DHCP respond with a unicast offer that includes addressing information the client can use. The client broadcasts a DHCP request to tell the server that the client accept the offer. The server respond with a unicast acknowledgement accepting the request. DHCP attack. DHCP spoofing attack occur when a rogue DHCP server is connected to the network and provide false IP configuration parameter to legitimate client. A rogue server can provide a variety of misleading information. All right. Okay, wrong default gateway. Threat actor provide a valid IP. Provide an invalid IP gateway or the IP address of each host to create a middleman in the middle attack. This may go entirely undetected as the intruder intercept the data flow through the network. And then wrong DNS server. Threat actor provide an incorrect DNS server address pointing the user to a malicious website. Wrong IP. Threat actor provide an invalid IP address, invalid default gateway IP address. So the actor then create a DOS attack on the DHCP client. Assume a threat actor has successfully connected a rogue DHCP server to switch port on the same. Yeah. All right. Okay. So assume that threat actor has successfully connected a rogue DHCP server to a switch port on the same subnet as the target client. The goal of the rogue server is to provide client with false IP configuration information. The client broadcasts a DHCP discover request looking for a response from a DHCP server. Both server receive the message. And then the legitimate and raw DHCP server each respond with valid IP configuration parameters. The client replied to the first offer received. Third one, the client received the raw offer. First, it broadcasts a DHCP request accepting the parameters from the rogue server. The legitimate and rogue server each receive the request. But only the rogue server unicast to reply to the client to acknowledge its request. The legitimate server stop communicating with the client because the request has already been acknowledged. Okay, this one a lab. So you can do as well this packet tracer. Yeah. Sorry, this one a lab. Explore DNS traffic. Yeah, in this lab. Okay, physical. Okay, all right. Network security best practices. So confidentiality, availability, and also integrity. Yeah. So network security consists of protecting information and information system from unauthorized access, use, disclosure, disruption, modification, or destruction. Most organizations follow the CIA information security tribe, confidentiality, integrity, and availability. For confidentiality, only authorized individual entities or processes can access sensitive information. It may require using cryptographic encryption algorithm such as AES to encrypt and decrypt data. Integrity refers to protecting data from unauthorized alteration. It requires the use of cryptographic hashing algorithm such as HA. Availability, authorized user may have uninterrupted access to important resources and data. It requires implementing redundant services, gateways, and also links. The defense in-depth approach. To ensure secure security across both public and also private network, you must secure devices including routers, switches, servers, and hosts. Most organizations employ a self-defense in-depth approach to security. It requires a combination of network devices and services working together. Yeah. Several security devices and services are implemented like VPN, firewall, ASA firewall, IPS, SA/WSA, and AAA or AAA server. All network devices, including the router and switches, are hardened. You must also secure data as it travels across various links. A firewall is a system or group of systems that enforces an access control policy between networks. Okay, so this one allow from external address to the web server, traffic to FTP, traffic to SMTP, traffic to internal IMP server. Okay, all right. This is a firewall. Try to this one filtering. Deny. I mean they will protect. Filtering. Yeah. IPS. To defend against fast-moving and involving attack, you may need cost-effective detection and prevention system integrated into the entry and exit point of the network. IDS and IPS technology share several characteristics. IDS and IPS technology are both deployed as sensor. An IDS or IPS sensor can be in the form of several different devices. First, a router configured with Cisco iOS IPS software. Third, a device specifically designed to provide dedicated IDS or IPS services. A network module installed in an adaptive security appliance. Switch or router, yeah. And IDS and IPS technology detect pattern in network traffic using signature. When it is set of rule that used to detect malicious activity, DNS and IPS technology can detect atomic signature pattern or single method or composite signature pattern multi-pack. The figure shows how an IPS handles denied traffic. The threat actor sent a packet destined for a target laptop. Yeah, the IPS intercept the traffic and evaluate it against known threat and the configured policies. The IPS send a log message to the management console. The IPS drop the packet. Okay, content security devices. The Cisco Email Security Appliances or ESA is a special device designed to monitor SMTP or Simple Mail Transfer Protocol. The Cisco ESA is constantly updated by real-time feeds from the Cisco Tilos. This threat intelligence data is pulled by the Cisco ESA every 3 or 5 minutes. The Cisco Web Security Appliances WCA is a mitigation technology for web-based threat. The Cisco WSA combines advanced malware protection, application visibility, and control, acceptable use policy control and reporting. Cisco WSA provide complete control over how users access the internet. The WSA can perform backlisting of URL and URL filtering, malware scanning, URL categorization, web application filtering, and encryption, and also decryption of web technology. Cryptography. All right. So we go to the video regarding crypto.
Hello, everyone. We are here to secure our communications. That means our organizations need to provide security for data that is stored on our machines as well as moving across network links. Well, to get started, we're not just going to start sending data around. Let's start first by making sure our data is the correct data. For example, on my desktop, I have this folder titled Important. And in this Important folder, I've got these 6 files. Now, how do I make sure these 6 files that have data inside them have not been maliciously altered or changed since I last used them? Well, that's called hashing. It's part of data integrity. What I can do is open up another program, for example, this one, Quick Hash, and I can go to that directory and I can select the directory of important where all those files are in. If I go into important and click select, this program is going to hash all of those files. And due to the exact bits of data in each file, you will get a specific hash value that correlates to that file. But what would it look like when those files have been altered? How can I check that? For example, maybe financial records or employee passwords. Is I can go to an individual file and select it in this hash program. How about we do employee passwords? And it will give me a hash output. Now what I can do is I can go into this file of employee passwords and I'll change it by 1 character. To change it by 1 character in employee passwords, how about Dragon 0 becomes Dragon 00, 2 zeros. What I'll do is save the file, employee passwords. We're going to go back into that hashing program and we're going to take a look at how this hash is about to change. Before it was 6.5 in the beginning, 4.6.3 at the end. Let's go to the employee passwords file one more time. Take a look at this. It is completely different. And to compare it, I'm going to paste in here what I expected the hash to be, what it should have been if it didn't change. The program says this does not match the previous hash. If you compare those two, they are completely different just by adding on an extra 0. So this is data integrity using hashing. What we're going to look at now next is the idea of encryption. And what we want to verify here is that when we move our files from one place to another, it's nice to know they haven't been modified using integrity and hashing, but it's also nice to know that they haven't been intercepted and viewed. So we need to encrypt these files. Now to do this, I'm going to use an open source program known as 7-zip. And with 7-zip, I have it looking at that directory marked as important. And I will take a couple files. How about employee passwords and employee records? I'll take these two. I'm going to right click on them. I'm going to put them in an archive with 7-zip. And this is going to give me some options. The options first is to name the file. I'm just going to name this file as secure.7zip. And for the password, which is going to be a symmetric encryption password, I'm going to use super secure. And this is going to encrypt files inside of this new file known as secure.7z. And in order for people to decrypt and view these files, they'll have to have the encryption password of super secure. Since it's the same password used to encrypt and decrypt, that's known as symmetric encryption. I'll click OK, and we're going to encrypt those two files. First one's done, and second one's done. So I've got this new file, secure.7z. And in order to gain access to it and view the confidential data inside of it, I have to right-click, go to 7-zip, and I'd say extract to secure. From there, I get my password pop up in order to decrypt the contents, and that will be the password again of super secure. So you can see it, and I'll click OK. From there, it's going to open up a new directory right here. It's decrypted those files, and now those files are right here. If I wanted to now, I can verify these files have not been altered in transit, and that would be by using my hashing program for data integrity. So cryptography here is going to provide you data integrity, origin authentication, making sure a message is not a forgery and it actually comes who it said it came from. Data confidentiality, which is our encryption and making sure that if data is intercepted, it can't be deciphered. And also non-repudiation, where it guarantees that the sender cannot refute the validity of their message. They are the one who originally sent it and they have signed off on it.
All right, thank you. Okay. Okay, that's regarding cryptography. Okay, securing communication. Organization must provide support to secure data as it travels across a link. Yeah, this may include internet traffic, but is even more important to protect the data that travel outside of the organization. These are the four elements of secure communication. First, data integrity. Second, origin authentication. Third one, data confidentiality. And fourth one, data non-repudiation. Yeah. Okay, data integrity. Data integrity guarantees that message was not altered. Integrity is assumed by implementing either MD5 or message digestion version 5 and secure hash algorithm, hash generating algorithm. So origin authentication guarantee that the message is not forgery and does come from whom it states. Many modern networks ensure authentication with protocols such as hash message authentication code HMAC. Data confidentiality guarantees that only authorized user can read the message. Data confidentiality is implemented using asymmetric and symmetric and asymmetric encryption algorithm. And finally, data non-repudiation guarantee that the sender cannot repudiate or refute the validity of message sent. Non-repudiation rely on the fact that only the same sender has the unique characteristic or signature for how that message is tracked. Cryptography can be used, almost everywhere or anywhere that there is a data communication. In fact, the trend is toward all communication being encrypted. Data integrity. Hash functions are used to ensure the integrity of message. They guarantee the message that they guarantee that message data has not changed accidentally or intentionally. In the figure, the sender is sending 100 money transfer to a lakh. The sender wants to ensure that the message is not altered or on its way to the receiver. The sending device input the message into a hashing algorithm and compute its fixed length hash of this, yeah. And this hash is then attached to the message and sent to the receiver. Both the message and the hash are in plain text. The receiving device remove the hash from the host and input the message into same hashing algorithm. If the computed hash is equal to the one that is attached to the message has not been altered during transit. If the hashes are not equal, then the integrity of message can no longer be trusted. Hash function. There are three well-known hash functions. MD5 with 128-bit digest, which is MD5 is one-way function that produces 128-bit hash message. MD5 is legacy algorithm that should only be used with no better alternative are available. Use SHA-2 instead. SHA hashing algorithm, HA1, very similar to MD5 techniques. Since, SHA1 creates an 160-bit hash message and is slightly slower than MD5. SHA1 has known flaws and is a legacy algorithm used SHA-2 when possible. So SHA-2, this includes SHA-2224, SHA-256, SHA-384, SHA-517, SHA-256, SHA-384, and SHA-412, a next generation algorithm, and should be used whenever possible. While hashing can be used to detect accidental changes, it cannot be used to guard against deliberate changes. This mean that anyone can compute a hash for any data if they have the correct hash function. Therefore, hashing is vulnerable to man in the middle attack and does not provide security to transmitted data. Okay. Okay. Origin, yeah. Origin authentication. To add authentication to integrity assurance, use a key hash message authentication code. And HMAC is calculated using cryptographic algorithm. Yeah, that combines a graphic hash function with a secret key. Only parties who have access to that secret key can compute the digest of an HMAC function. This defeat man in the middle attack and provide authentication of the data origin. Data confidentiality. There are two classes of encryption used to provide data confidentially. These two classes differ in how they use keys. Symmetric encryption algorithms such as DES or 3DES and advanced encryption standard AES are based on the premise that each communicating party knows the free share key. Data confidentiality can also be ensured using asymmetric algorithm, including reverse Shame and Edelman, RSA, and the public key infrastructure, PKI. The figure highlights some differences between each encryption algorithm. So symmetrical encryption use the same key to encrypt, and for asymmetrical encryption, use different key to encrypt and encode data. Okay, for asymmetric, key length are about 40 to 256. So key length are long 512 till 4096 bits. Okay. All right, faster than asymmetrical algorithm, commonly used for encrypting bulk data such as in VPN traffic. Computational tasking be therefore slower than symmetrical encryption. Commonly used for quick data transactions such as HTTPS when accessing your bank data. Symmetric encryption. Symmetric algorithm use the same pre-share key, also called a secret key. To encrypt and decrypt, a pre-share key is known by the sender and receiver before any encrypted communication can take place. Symmetric encryption algorithm are commonly used with VPN traffic because they use less CPU resources than asymmetric encryption algorithm. When using symmetric encryption algorithm, the longer the key, the longer it will take for someone to discover the key. To ensure that the encryption is safe, use a minimum key length of 128 bits. So, symmetric encryption algorithm, we have dash, triple dash, AES, seal, and also reverse cipher or RC series algorithm. Okay, the encryption, you can go through this for each of the algorithm. Asymmetric encryption. Asymmetric algorithm, also called public key algorithm, are designed so that the key that is used for encryption is different from the key that is used for decryption. Asymmetric algorithm use a public key and a private key, both. The complementary pair keys is required for decryption. Data encrypted with the public key require the private key to decrypt. Asymmetric algorithm achieve confidentiality, authentication, and integrity by using this process. Because neither party has a shared secret, very long key length must be used. Asymmetric encryption can use key length between 512 to 4096 bit. Key length greater than or equal to 1024 bit can be trusted, while shorter key length are considered unreliable. Example of protocol that use asymmetric key algorithm such as Internet Key Exchange, IKE. This is a fundamental component of IPsec and VPN. Secure socket layer, this is now implemented as IETF standard transport layer. Security, TLS. Third, secure shell, SSH. This protocol provides a secure remote connection to a network. So PGP, pretty good privacy. This computer program provide cryptographic privacy and authentication. It is often used to increase the security of email communication. Asymmetric algorithms are substantially slower than symmetric algorithm. Their design is based on computational problems such as factoring extremely large number of computing discrete logarithm of extremely large numbers. Because they are slow, asymmetric algorithms are typically used in low volume cryptographic mechanisms such as digital signature and also key exchange. Okay, this is asymmetric encryption. This is the number of algorithm. Okay, and number of the key length together, and this one some description. You can go through each of these. What you call encryption, asymmetric encryption algorithm. Okay, Diffie-Hellman. Diffie-Hellman DH is an asymmetric mathematical algorithm where two computers generate an identical shared secret key without having communicated before. The new share key is never actually exchanged between the sender and receiver. Here are three examples of instances when DH is commonly used. Data exchange using IPsec VPN. Data encrypted is on the internet using SSL or TLS. SSH data is exchanged. DH security use unbelievably large number in its calculation. Unfortunately, asymmetric key systems are extremely slow for any sort of bulk encryption. Therefore, it is common to encrypt the heart of the traffic using a symmetric algorithm such as 3-dash AES, and then use the hash algorithm to create key that will be used for encryption algorithm. The color in the figure will be used instead of number. To simplify the DH key agreement process, the DH key exchange begins with Alice and Bob agreeing on arbitra, arbitrary common color and does not need to be kept silent or secret. The agreed upon color in our example is yellow. Yeah. Next, Alice and Bob will each select a secret color. Alice choose red while Bob choose blue. This secret color will never be shared with anyone. Yeah. The secret color represents the chosen secret private key of each party. Alice and Bob mix the shared common color. For example, yellow with their respective secret color to produce a private color. Therefore, Alice will mix the yellow with her red color to produce a private color of orange. Both will mix the yellow and the blue to produce a private color of green. Alice sent a private color orange to Bob, and Bob sent back his private color green to Alice. Alice and Bob each mix the color they receive but with their own original secret color. Yeah. The result is final. Is final. What? Okay. Alright, the result is a final brown color mixture that is identical to other final color mixture. The brown color represents the resulting share secret key between Bob and Alice. Alright. Okay, that's all. This one module practice and quiz. You can go through if you want. Just check your understanding. Alright, thank you for watching and listening.